So this problem is one to help us figure out how to find probabilities using the central limit theorem and sampling distributions. In this case, we were told we have a hummingbird egg. We're looking at the incubation time of that Allen hummingbird eggs. We do know from some back research that the random variable has a mean of 16 days, and we are going to assume that the standard deviation is approximately 2 days. The distribution of the random variable is more or less mound-shaped and symmetric, but not normal. Suppose we have 30 eggs in the incubator and we want to look at some probabilities and information. So the first thing with most problems is to write down what your random variable is. Again, that's what you measured. So in this case, they were measuring the incubation time of the Allen hummingbird egg. Now in this problem, we are going to also look at the sample mean, and which is the average or mean incubation time. So it doesn't hurt to write that down. Remember, the symbol for sample mean is x with a bar over top of it, so x bar. And that would be the mean incubation time of the Allen hummingbird egg. Now, in order to do probabilities with this, which is most likely what we're looking to do, we have to know what the sampling distribution of the sample mean is. This is akin to just looking at drawing a axis here that is called x bar and figuring out what picture we can draw above this. So we can go back to our original random variable, but we are told that it's not normally distributed. So since we're told it's not, we have to have a certain sample size to be able to ensure that it is normally distributed. The central limit theorem tells us that as n increases, the distribution of x bar will look more and more normally distributed. The rule of thumb is 30 or more, and we notice that we had in fact 30 in this example. So n equals 30, so that tells me that x bar is normally distributed, most likely. So what that really means is I can draw a normal curve over top of the x bar axis. We would like to know what the mean and standard deviation of the sampling distribution is. So that means we want to know the mean of x bar. The mean of x bar is the same as just the mean. So we were told that the mean is 16 days. So the mean is 16. The standard deviation is a little different because it actually gets smaller as you have more and more a larger and larger sample taken. So you take the original standard deviation and divide by the square root of n to get a value that gives you a little bit more understanding of what's happening and gets you less variability. So we are told that the standard deviation is 2 days, and our sample size we already said was 30. So this is approximately 0.365. So now that we have all that information, we can find some probabilities. The first probability we want to find is what is the probability that the sample mean is between 16 and 17 days. You want to rewrite that statement in a mathematical terminology. So probability would be P of sample mean being between means that you'd have 16 is less than x bar is less than 17. We can go ahead and look at a picture of this. From what we just did, we know we can draw a normal curve here. We know that its center is 16 because that's its mean. 17 falls to the right of that. And we want to be between, so we just shade the area in between. Now we can use any technology to find this. If you're using the TI-83 or 84, then you would use normal CDF. Our lower limit where the shading starts is 16. Our upper limit where the shading ends is 17. Our mean is 16. And our standard deviation is either the 0.365 or to have less rounding error, you can actually type in 2 divided by the square root of 30. So we'll go ahead and do this calculation on our calculator. And so we end up with let's see here. Almost there, sorry. And we end up with approximately 0.4969. So it's a pretty high probability. So it tells us that almost 50% of all of the sample means would be between 16 and 17. So if you took a whole bunch, or in this case 30 hummingbird eggs, and you found their sample mean length of incubation time, you would actually find you'd have a 50% chance of getting that kind of sample means between 16 and 17. Now let's do one more. What is the probability that the sample mean is less than 15 days? So again, we want to rewrite this in a mathematical statement. Probability that the sample mean is less than 15. Again, you want to draw a picture. The center of this picture is 16. 15 falls to the left of it. And we want to be less than, so we're going to shade to the left. Again, you can use any technology you want to find this probability. If you're using the TID3s, then the shading starts really, really low, or what we call negative infinity. So we do that as -1 E99 on your calculator. It ends at 15. The sample mean is 16. And again, you would then type in 2 divided by the square root of 30 to get your probability. So we'll go ahead and type that into our calculator. And we come up with a probability of approximately 0.0031. Notice that that probability is incredibly small. The range, not the range rule of thumb, but the rare events rule of inferential statistics says that if your probability is smaller than, let's say, 5%, you have an unusual event. So in this case, it would be very unusual to find a sample mean less than 15 days. Let's say you actually did find a sample mean less than 15 days. That might actually say to you that something that you assumed is wrong. The only thing we assumed in this problem is that the sample mean is 16 days. So it could be that your sample mean is actually less than 16 days if you actually found a sample mean less than 15.